So good afternoon, everybody, and welcome back to the Peace Seminars. First of all, I would like to thank you all for being here today to hear about Pol Alsina's research. Pol is a PhD student at the University of the Basque Country, and he's going to talk about J-coupling NMR spectroscopy at high magnetic fields with NV centers. So thank you two very much, Paul, and the floor is yours whenever you're ready.
Okay, thank you, Angela, for the introduction. And yeah, as you said, I'll try to introduce more than go into detail. It will be a very basic talk about the title that you just read. If anyone has any question during the talk or afterwards, I don't know how this works, just interrupt me or wait until I finish. First, let me apologize beforehand because I'm feeling a bit sick today, so I might cough during the presentation. I'll try not to, but yeah. So yeah, well, as usual, I'll start with a simple introduction just for you to know what's the state of the art of standard NMR and why we want to translate it to or use it in the field of nitrogen vacancy centers. Once I've done so, I will introduce the most interesting intramolecular interactions, which in the end is what it's the target in any NMR experiment. You want to detect those interactions to know something about your sample. And well, we will talk a little bit about realistic conditions in a real experiment, because that's the whole point of our works. Yeah. Afterwards, I'll explain very hand-wavy, let's say, our first work in this direction, which was done almost a year ago. But this will serve me to introduce pulsed sequences, which basically what you do is send radiation in a given way to your sample, so it behaves as you want, and it encodes the information about the dynamics that you in the end want to recover with your sensor, in our case with the NV sensor, but it's the same way as in standard NMR. And the last part of the talk will be I will present our latest work, which is basically, just as a brief introduction, how to use hydrogens as emitters for any kind of interactions, which you will see that it can lead to improvements. At least that is what we expect to the expected results. Okay, let me set the timer, which I forgot. And of course, well, as usual, I will finish with an outlook and the conclusions of the talk. Okay, so first, conventional NMR. Now, this technique has been around for a lot of years, almost 100 or so, and it can be used in a lot of different fields. For example, organic chemistry, catalysis, biology, medicine. When you go to the hospital and you take a magnetic resonance, that's what they do. For example, magnetic resonance imaging, or it has a lot of different interests in industry. Now, one of the catches, not catches, but one of the restrictions of this technique, as this schematic figure shows, is that you usually require large samples for your sensor, which in the case of conventional NMR are coils, standard coils. So you require those samples to be quite large. Actually, they need to be macroscopic. What happens if you start to decrease the size of your sample? So the size emitted by it starts becoming weaker and weaker, and there's a point where your the coils are no longer able to detect such weak signals. So this is a restriction, because if you want to go to a smaller sample size, there's a point where standard NMR cannot reach. So yeah, this, in other words, it means that this technique has bad sensitivities, because you only can measure macroscopic samples. Apart from that, in these techniques, but also in ours with NV centers, you usually require of strong and homogeneous magnetic fields, and that I will explain why is that later. But the important thing is that they need to be quite homogeneous in space, because if not, I will explain it later as well, but your signals start to get a bit messy, and in the end, it results in worse signal to noise ratio. So even though they have these issues, these techniques, they are very commonly used and they are quite important. But I presented the issues so that I motivate a little bit the use of nitrogen vacancy centers instead of NMR. So first of all, what's a nitrogen vacancy center? So maybe you've heard, maybe you didn't, but basically you have a diamond lattice, and at some points you have a spin defect where basically, effectively, you have a spin one half system. I won't go into more detail, but you can have a lot of them in your diamond lattice. And the important thing with that is that you can control them. So you can initialize and read them with good responses, and you can control them coherently as well. And if you have a lot of them, you, as this scheme depicts, you can have a lot of them stacked together. And effectively, it can be demonstrated that you can measure anything that is placed exactly on top of the diamond surface. Now, here comes the first advantage of this, because since all of the MV centers usually are placed quite near the diamond surface, the signal emanated from whatever sample do you have there will be much stronger for them. So in principle, since the signal is much stronger, you can reduce the sample quite a lot compared to standard NMR, and you can still measure that signal. So in other words, again, their proximity to the sample makes them very sensitive to the sample. So you can reduce a lot the volume that you want to study. Now, another trait of them is that they have great spatial resolution, meaning that you can distinguish up to single cell volume. So if you have different cells there, maybe you can distinguish between them, the difference that there may be between one cell and the other. So this is quite a good trait which again, it's quite difficult in standard NMR. And apart from that, well, they can be used at extreme conditions such as high pressure, for example. And these kind of conditions are usually carry some issues when working with conventional NMR. So this is a bit the motivation of why use MV-based NMR instead of conventional NMR. Okay, now, why in both techniques, I don't know if I said that, but in both techniques, we require usually strong high magnetic fields. Why is that? And homogeneous. Well, the ideal state in both cases of our sample, each spin of our sample would be this one, the completely polarized state. So each spin, we would like it to be at the ground state or excited state, it doesn't matter. But reality, it's a bit more complicated. And in reality, the state is something like this, right? Where this alpha parameter right here is what's called the Boltzmann constant, which depends on other constants such as the h-bar, the Planck's constant. This gamma right here is the gyromagnetic-ratio, which is different for each nuclei. For example, hydrogen and carbon, the value of this gamma parameter is different. This is the magnetic field that you apply to the sample. K is the Boltzmann constant and T is the temperature. Okay, knowing this, notice one thing. If I don't apply a magnetic field, my state will be the completely mixed state. Now, this state is completely useless because during the dynamics, it will not gather any information whatsoever about the interactions that I want to detect. So that's why we need a magnetic field. And why it has to be strong? Well, if it's strong, compared to the other constants in this parameter, my state tends to be the ideal state. Now, in the ideal state, the information accumulated throughout the dynamics, it's the maximum possible. While in the middle between the mixed state and the ideal state, the information is quite in the middle point. So it's not all the information is useful. So that is why in both cases, both MV and standard NMR, we are interested in applying a magnetic field as high as possible. All of this, I repeat, as I said before, higher magnetic field implies higher initial polarization of your sample. So in the end, it will lead to better sensitivities or better signal to noise ratio. Okay, now that we know this, let's understand or let's try to elucidate what interactions are interesting. Imagine a very simple molecule, schematic in this case, where there are two hydrogens, which are spin 1/2 systems. And let's forget of the rest of the molecule for simplicity, because I just want you to understand the interactions playing a role here. Now, if I apply a magnetic field in the Z direction, for example, the first interaction that we have to take into account is the Zeeman interaction, which is basically a splitting in the energy levels of each spin. Now, if there wasn't anything else, this would be the resonance frequency of each spin. As in this case, both spins are hydrogens, in principle, both frequencies are the same. Now, what happens in molecules? When inside a molecule, each hydrogen has its molecular environment. This means that each hydrogen will be surrounded by a lot of different nuclei, which at the same time will generate slight magnetic fields that will affect the magnetic field that I'm applying. So in the end, the effective result is that the magnetic field that one hydrogen and the other will feel will be slightly different than the one that I am applying. In this case, for example, for the first hydrogen, it will feel a magnetic field, which is the one that I'm applying, plus a small shift due to its environment. And the same for the second one. And here it's important to notice that these shifts, they do not need to be the same for both hydrogens, because each hydrogen has its own molecular environment. So it depends on each position. Okay, so this has to be taken into account in our Hamiltonian. So we adjust a shift to the Zeeman effect, like this one. Now, before moving further, how does this affect my signal? Okay, it will affect the frequency of each hydrogen. So at the same point, when I Fourier transform that frequency, it will affect the peaks where the frequencies are supposed to be. So the dotted line corresponds to the resonance frequency if no chemical shift existed for both hydrogens. Since both are hydrogens, both peaks should be at this dotted line. But if we consider now that there's a chemical shift for both hydrogens, and in the most general case, they are different, these shifts, both peaks will move from its original resonance frequency to another point in this frequency spectrum. And yeah, and I will have, instead of one peak, two peaks, one corresponding to each hydrogen. Now, this, more than a problem, it's a good thing, because chemists usually know a lot of the values of these chemical shifts. So if I know I have a table with, say, listed all the possible values of chemical shifts for all the possible molecules, and I perform an NMR experiment over a sample that maybe I don't know what is it, with this spectrum, I will know the value of the chemical shifts, and thus I will be able to know more about my molecule, which maybe before I didn't know. So this is one of the interactions that usually you want to target when performing an NMR experiment. Okay, and there's another interesting interaction in molecules that plays a role, and that is second-order spin-spin interactions among the different nuclei that you may have in your molecule. I say second order because it's not direct dipole interaction, but it's an interaction that is mediated through the electron cloud of the molecule. Okay, we believe that. But the important thing is that there's an effective 2I2 spin interaction between all the spins in my molecule. That also carries information of the molecule, because, well, with that, for example, I can elucidate distances between spins, or maybe the angle between the spins, or wherever. And the form that this interaction takes in the Hamiltonian is something like this. So it's a ZZ type interaction, and it's called J-coupling. Now, if I take the previous spectrum that only considered chemical shift, and now I add this type of interaction, you will see that what happens is that my peaks, the red before, get split each of them into two due to these new interactions. And actually, the separation between these two peaks corresponds exactly, sorry, to the value of the J-coupling. So like this, in the end, at the end of the NMR experiment, I would get a spectrum like the blue one, and this can tell me information about the chemical shift because it's the center point of all the peaks, and the separation between the peaks will give me information about the J-coupling. So this is more or less the idea behind any NMR experiment. Of course, there are experiments more complicated like this than this, but this is the basic idea and the most interesting interactions that you can find. Now, let me add here that throughout all the talk, I will only consider liquid state samples. If you go to solid state, there are other interactions that you may want to consider, but for now, we consider only liquid state. It's simpler, the case. Okay, so this is the simple case and a naive case. Let's move to a more realistic scenario. So this Hamiltonian that we've just seen, it's a Hamiltonian only for one molecule, but we have to assume that our sample is small, but not as small as to only contain one molecule. So it will contain a lot of different molecules, right? So the total Hamiltonian of the sample will be just the sum or the sum, either the sum or the average of all the Hamiltonians. Okay, good. But what happens? As I said at the beginning, we have to apply a magnetic field, right? And the experimental problem with magnetic fields, is that it's very, very difficult to make them completely homogeneous, especially. So this means that at different points in space, the magnetic field will have a different value, probably. And this is due to experimental issues. Now notice then that for each molecule, this term in the Hamiltonian will have a slightly different value because the magnetic field that it's there, it's different. So this term will be slightly different for each term for each molecule, sorry, in your sample. Now, the effect that this has is the following. So this is assuming the perfect case. So this is a signal that you would get assuming a completely homogeneous magnetic field, so equal everywhere. And this is the corresponding Fourier transform. This is what we've seen in the previous slide. But now if we consider the magnetic field inhomogeneities, what happens to the signal is this. So effectively, the coherence time of your sample reduces, and it reduces, as you can see, quite a lot. And the effect that it has to the spectrum is that your peaks become much, much wider. So before they were quite narrow, but now they are very wide. And this is due to the fact that your magnetic field is not homogeneous. So in the end, what happens due to the spatial inhomogeneities is that you get worse frequency resolution because you're not able, you're not good as knowing what is the frequency that corresponds to each peak as in the perfect case. So due to these inhomogeneities, you lose frequency resolution. So this is one of the issues of working at high magnetic fields. But as I said before, and I will repeat later, it's interesting because you gain a polarization and thus you gain sensitivity, signal to noise ratio. And this comes here. Now, this is the spectrum that we had considering inhomogeneities, but we have to consider as well sources of noise, such as white noise or shot noise. And in any quantum mechanics experiment, there is shot noise. So the spectrum actually would not look like this, but it would be something much more messier. So the spectrum would get much uglier. And this is due to the different sources of noise. So there are basically two main issues here, or two main things to consider. One is resolution, which is, I repeat, due to the fact that my magnetic field is not homogeneous along all the space or along my whole sample. And the other is due to the sources of noise, I get worse signal-to-noise ratio or worse sensitivity, which is basically defined as how tall are my peaks compared to the noise sources that I have. Now, let me go back again to the magnetic field. If you think about it, there's a trade-off. Because remember that I said, if you want to increase sensitivity or increase signal-to-noise ratio, you want to increase the magnetic field, right? But higher magnetic field implies worse spatial inhomogeneity, which means worse resolution. So it's like a trade-off between sensitivity and resolution, or the other way around, right? So this is kind of a problem, but well, you can prioritize one or the other. Now, let me mention that you can increase sensitivity or signal-to-noise ratio by increasing the number of measurements too. You just have to repeat the experiment more and more times. But the problem with that is that the relationship goes like 1 over square root of the number of measurements. So if you wanna, for example, improve your signal-to-noise ratio to, by 2, you will have to perform 4 times more measurements, which means an experiment that will be 4 times longer. So this is not a very good relationship. That is why usually it's more interesting to increase the magnetic field because it's linear. So it's if you increase twice the magnetic field, you will get twice a better signal-to-noise ratio. Okay, so very good. Now let's go a bit deeper into the protocols. And actually, let's go back to the single molecule Hamiltonian, because with that it's enough. And let's see what's a pi pulse and what does it do. Okay, a pi pulse, it's basically inversion of population. So if you have your population in the plus state, you apply a pi pulse and you end up with a population in the minus plus state. Okay, and why this is useful? Okay, so imagine that I have 2 spins, right? And I apply a pi pulse over both of them. And applying a sequence like this one. This is called the Haniko sequence or echo sequence. So I let the system evolve freely for a period, then I apply a pi pulse over both spins, and I let it evolve again freely. Okay, the effect of the pi pulses is quite easy to show that after the pi pulses, the effective Hamiltonian will look like this, which is basically very similar to the initial one, but notice how each spin operator changed its sign. So all of the terms will have changed the sign, except the term corresponding to the J-coupling, since, well, minus times minus, it's plus. So yeah, if I apply this sequence over my molecule right here, I will have that before the pi pulses, my effective Hamiltonian, it's the initial one, while after one, it's this new with some signs changed. So in the end, the effective propagator is just the concatenation of both of them. And if you do it, it's very easy. You end up that in the end, the effective only dynamics are the ones that correspond to the J-couplings. You cancel chemical shifts and you cancel the Zeeman interaction of each molecule. This is very nice because, yeah, you can target only the J-couplings. So this is quite useful. And let's see what happens now if I apply it only over one spin. So it's the same, just that the signs that will change will be only the ones corresponding to the spin 2 in this case, or spin B. So now if I do the same and I compute the effective propagator, now I will end up with this type of evolution right here, which notice that now I canceled the evolution corresponding to the J-coupling. So this is quite interesting because I can target specific J-couplings within the molecule. So say that I have a very complicated molecule and there are a lot of different J-couplings among all of the nuclei that I have there. But some of them are not interesting to me. So what I can do is apply just a pi pulse over one of the spins. So those non-interesting J-couplings will be canceled and I can focus only to the ones that interest me by applying 2 pi pulses over the spins that interest me. This way, my final spectrum will get much simpler. So this with complicated molecules is quite useful. So this is one of the functions of pi pulses in this scenario. And the other function actually is that they will cancel the effect of the magnetic field inhomogeneities throughout all the sample, which means in the end that they will improve the resolution of my spectrum. And that is why, if you remember, this term was the term causing causing the loss of resolution due to these inhomogeneities. But when I apply a pi pulse, remember that the effective Hamiltonian was something like this. So I don't care if this term is different for each molecule or not, because after the pi pulse or after that echo sequence, in the end, this term will not affect the dynamics. It doesn't matter if they are different for each molecule or not. So effectively, pi pulses improve as well the resolution of the protocol, even at high magnetic fields. So now I can work at high magnetic fields because I don't have the problem of resolution anymore. This is called as well dynamical decoupling, if anyone knows this concept. Sorry. Okay. Let's now move to the NV centers. Okay, so now remember, we focus in high magnetic fields. Now, until 2 years ago or so, sorry, it was quite different to work at high magnetic fields with NV ensembles. And that was very hand wavy because at high magnetic fields, the signals that you have to detect are quite strong, are quite fast, sorry. So it was very difficult to track them with the with the NV ensembles. So it was, oh my God, I'm sorry. It was very difficult to track those oscillations with your NV ensemble because you didn't have any sufficient power in your setup, experimental setup, to achieve so. But recently, well, 1 year ago or so, work by my colleagues got out that actually focused on measuring fastly oscillating signals, which means that now NV centers can be used even in the context of high magnetic fields. Now, very shortly, this is only the measurement part of the sequence. Now I will introduce the whole sequence, but just very shortly, this type of measurements allows the protocol not to be limited by the T2 of the sensor, in the sense that it will not affect the resolution, no matter how short it is, which is called quantum heterodyne detection. Yeah, as I've said, this is a measurement thought to work at high magnetic fields. And the basic idea is, okay, before this work came out, the idea was the following. So I have the Hamiltonian of my NV ensemble, and it depends of the signal of the sample, which in those cases, it depended it oscillated with a frequency which was very large, very, very large. So it was impossible to detect with the NVs. But thanks to this proposal now, the frequency that we are going to detect with our ensemble is controllable by us. We can set it at a desirable value, and the information will still be encoded now actually in the amplitude of the signal, but not in the frequency. Okay, so now let me introduce the first work that we did in this direction. Okay, so yeah, this is the basic sequence of that work. Okay, so part by part, first, imagine you have a molecule, so each horizontal line here corresponds to one spin. So here, for example, this one corresponds to a given hydrogen present in your molecule, and this one corresponds to the rest of the nuclei. And this line corresponds to the MV ensemble. Okay, so first, what we are going to do is a Nico sequence, as I explained before, and this sequence will encode in the state of the hydrogen the dynamics corresponding to only to the J-couplings. Remember that with this we kept only the information about the J-coupling. If you want to know what happens to the state more visually, you can imagine in the Bloch sphere the state of the hydrogen is placed in the X eigenstate, and then thanks to the evolution of the J-coupling, this state will move always on top of this axis, oscillating only like this, right? And the frequency of this oscillation will correspond to the value of the J-coupling. Okay, once I've done this encoding period, it's time to read. And to read the hydrogens with the NV ensemble, what we do is apply driving about the y-axis, and the state, wherever it was, will start to oscillate about that axis, right? The thing with this oscillation of the state is that it will start emitting a magnetic field that it can be tracked by the MV ensemble. And since the frequency of the driving that we're applying, we choose it, the frequency of this emitted magnetic field will also be chosen by us. So this is how you track this with the MV ensemble. Okay, and then the next step is just apply again another encoding period. So the state, it evolves again under the effect of the J-coupling, and then you measure again. The amplitude of that oscillation will have changed in principle because your state will not be the same as in the first measurement, and you measure again with the MV ensemble and so on. And that way you can reconstruct the evolution thanks to the J-coupling during the encoding periods. All right, now let's go to a specific case. Maybe it's easier to understand. So let's assume a hydrogen cyanide molecule because it's a simple molecule. And well, there's two J-couplings here, the one between the H and the carbon, and the one corresponding to the carbon and the nitrogen. Now this would be the sequence that I just showed, but for this case. So this is the encoding or loading period in this case. So notice how I apply the pi pulses and I let the system evolve. And then I read the hydrogen by applying a radiation to them. And that the magnetic field emanated during this period will be tracked by the MV ensemble by applying some pulses. This does not matter, but what matters is that I will the phase accumulated by the MV ensemble will depend on the amplitude of this emanated magnetic field from the hydrogens, which we call that at the same time, it depends on the evolution here. Okay, so yeah, this is what I just said. During the loading period, I have this Hamiltonian corresponding to the chemical shifts and the J-couplings, but recall that, yeah, with the pi pulses, I cancel the chemical shifts, I only keep the J-couplings, the one corresponding or between the hydrogen and the carbon, and the other one corresponding to the carbon and the nitrogen. Now, here there's a catch, and that's the following. Since in the end I will only read the hydrogen, I will only be able to detect the J-coupling corresponding to the hydrogen. So even though in my Hamiltonian I still have this term right here, this will not encode in the state of the hydrogen because this will only affect the state of the carbon and the nitrogen. So in principle, with this sequence, I can only detect J-couplings that are related to the hydrogen. So what now? What if I want to detect the other coupling? Well, the easy answer is, okay, so instead of reading the hydrogen, just read the carbon, right? And yeah, that's true. You just have to exchange the hydrogen and the carbon here, and then read the carbon. Okay, so far so good, but the problem comes now, and that is in the detection stage. The detection stage, as I said, the nucleus over which you're applying the radio frequency, the radiation, will emit a magnetic field, and that will be tracked with the MV, as I showed here. Now, the signal has this expression right here. Don't worry. I just want you to focus on this this term right here carries the information about the evolution during the loading period, okay? And then this term right here depends on which nuclei I'm reading. So in this case, this is the gyromagnetic ratio of the hydrogen because I'm reading the hydrogen, and this is the frequency at which that hydrogen is oscillating in this period. So the frequency of this emanated magnetic field. Okay, but if I read now the carbon, it happens that the signal is emitted by the carbon, it's much, much weaker and much slower. So if I read for the same time with the MV, notice how the shaded yellow area is the phase that the MV will accumulate during the detection stage, and it will be much smaller than in the case of the hydrogen. And that is why, and that is because, sorry, in the expression of the amplitude of the signal, you have to exchange these terms by the corresponding to the carbon. So in this case, the gyromagnetic ratio of the carbon is much lower than the one corresponding to the hydrogen, and as well the frequency of the oscillation. But this term, which recall it's the one that carries information about the evolution during this period, is the same. So the frequency, I mean, the state is the same, but the amplitude of that state will not be the same. And that is because the gyromagnetic ratio of the carbon is lower than the one corresponding to the hydrogen. Now that is a bad thing because hydrogen is the one with it's the one with highest gyromagnetic ratio, meaning that if I want to read any other nuclei, for sure I will get lower amplitudes, because this means, yeah, the amplitude, the phase acquired by the MV will be lower in any case that it's not hydrogen. And worse amplitude in the end means worse sensitivity or worse signal to noise ratio. And this can be easily seen if we look at a simple example. So here the blue signal corresponds to the one measured through the hydrogens, while the red one corresponds to the one measured through the carbon. Notice that they have the same frequency, but the amplitude of the carbon is much lower. So the Fourier transform of these two signals actually gives the same peak. So there's no problem, but the problem comes when I add realistic conditions to it. So when I add noise. So if I add noise, notice how the signal turn from this into a very messy thing, okay? But if you focus now on the Fourier transform, look only to the blue line, to the blue peak, which corresponds to the hydrogen. Notice how here the blue peak is still able to tell us which frequency is the one corresponding to the oscillation, while the one coming from the carbon is a complete mess, and we are no longer able to elucidate which peak is the correct one. And this is due to the noise, and the initial cause is that the amplitude of the signal was much smaller. So the usual approach here is, okay, so what I'm going to do is perform more measurements in the case of the carbon so that I achieve the same signal to noise ratio. Okay, but as I said, the relationship goes like this. So to achieve the same signal to noise ratio as in the case when I'm measuring the hydrogens, I would have to perform an experiment much longer, because the relation between the times is this one, and recall that the amplitude of the hydrogens is much higher than the one corresponding to the carbons, and there's a square here just on top of that. So just for you to see some numbers, if an usual experiment with hydrogens takes 1 hour, and I assume that the ratio between amplitudes is 4, which is quite conservative. I mean, it's either 4 or more. The experimental times that I would need for achieving the same signal to noise ratio would be 16 hours. So it's quite longer. It's 16 times longer, my experiment. So yeah, and this is the usual approach. I mean, usually there's no way around that. Okay, so now here comes our newest work, which we believe will be able to improve this fact by a lot. Okay, so remember, let's keep the same molecule and remember these two phase acquisitions. And okay, so the idea is the following. Can I measure the J-coupling, in this case corresponding to the carbon and nitrogen, but throughout the hydrogen, leveraging its higher amplitude? Well, the initial sequence was like this, and our proposal is to modify it or to invent a new one that looks like this. Okay, so it looks much more complicated, but actually it's the same sequence, but we just added these three new transfer stages, which actually what they do is, okay, let's go step by step. The first one, it correlates the state of the hydrogen and the carbon. Then notice how I apply, again, a loading period where, yeah, during this period, I estoy dando una charla. Lo siento. Sorry about that. So I apply here, again, the loading period as in the simple sequence. So in principle here, the information about the J-coupling will be encoded in the state of the carbon and the nitrogen. But since now, thanks to this stage, the hydrogen and the carbon are correlated, this information will be encoded as well in the state of the hydrogen. Now, this second transfer stage is needed to uncorrelate the hydrogen and the carbon again. So then I can read it perfectly, the hydrogen. And then this last transfer rewind stage is needed for that the signal in the end is simpler. If anyone wants more details, ask me. Okay, and the difference here is, as I said, that the shaded area, which in the end is proportional to the amplitude of the signal in the end, is much greater in this case than in the case where I read carbons. So this is our proposal or our sequence proposal to improve signal-to-noise ratio when you want to measure things that are not related to hydrogen. And to check if that was correct or not, we simulated for a more complicated molecule. So notice that this molecule has a lot of hydrogens. And let's check if this works when I want to measure the coupling between the carbon and the phosphorus in this case. So the results are this. So in the signals, the yellow circles correspond to directly measuring the carbon. So notice how the amplitude is quite small. And the red circles, the red crosses correspond to applying our sequence, our new sequence to the hydrogen. So in the end, I end up by reading the hydrogens. And it turns out that the amplitude is much, much higher in this case. So in principle, it works. We tried to simulate a real experiment. So in principle, this is as close as we can be to reality. And well, yeah, this improvement, maybe it's better seen here in the Fourier transform, where the peak obtained with our proposal is much higher than for when using the simpler sequence for the carbons, which leads to higher signal-to-noise ratio. Now, in this case, just to put some numbers, if I assume, for example, a decoherence time of my MV ensemble of 20 microseconds, the signal-to-noise, the ratio between signal-to-noise ratios is 16 between our proposal and the one corresponding to the simpler sequence, meaning that our signal-to-noise ratio is 16 times better than the previous one, which leads to an experimental time a shorter experiment by a factor of 256 times to achieve the same signal-to-noise ratio. So our experiment with this new sequence would be about 2 orders of magnitude shorter, but we would achieve the same signal-to-noise ratio. And this is quite dependent on the decoherence time of the MV ensemble. So if instead of 20, I put 10 microseconds, this ratio explodes and becomes 40 instead of 16. So the experimental time improvement can reach 3 orders of magnitude. So our experiment would be something like 1,000 times shorter to achieve the same signal-to-noise ratio. So as you can see, these results are quite promising. Of course, these are simulations. In reality, a lot of things can happen. And I guess the results of the experiments would not be as good as this. But even though even that we consider quite realistic conditions. So we expect it to be good too in a real experiment. And this is for you to notice the relationship between the improvement in the experimental time versus the decoherence time of the MV ensemble. So for short decoherence times, our sequence is much better because hydrogens oscillate much faster, leading to higher signal-to-noise ratios or to the same signal-to-noise ratio but with less time, maybe with 5 microseconds, which is a usual value in experiments for the T2 of the MV ensemble. We can reach up to almost 6,000 improvement, a factor of 6,000 reduction in the experimental time. While if it gets larger, the T2 of our MV, notice how this improvement reduces. Now, you cannot see it here, but our proposal, it's always better in the sense that the value is that no matter the T2, even if it increases a lot, the improvement will at least be 16. So this means that this line tends to 16. So no matter the decoherence time of the sensor, our sequence will always lead more or less to a 16 times improvement in the experimental time to achieve the same signal-to-noise ratio. And with that, I finish. Let me conclude very fast. So I presented a versatile in the sense that I can choose what interactions I want to detect protocol that works at the microscale. And recall that this is only true for liquid state NMR. We use an heterodyne-like measurement, meaning that the T2 of our NV ensemble does not affect the resolution of the signal in the end. It's a protocol that works at high magnetic field, so this even increases further the sensitivity or the signal-to-noise ratio. And the last 2 slides, I presented our newest work, which is almost published, but not yet. We are still working on it. That it seems that we found a way to improve signal-to-noise ratio or experimental time by at least 2 orders of magnitude with respect to the state-of-the-art approaches when it's time to detect things that are not related to hydrogens. And just the outlook, now the next step would be, instead of using hydrogens as emitters, use electrons, because electrons emit much stronger than hydrogens. So in principle, the improvement would be even better if using electrons. But with electrons, some issues come into play. So this is just an idea. We haven't thought very much about that. But this is one of the paths that we can take. And the other one is to apply all of these protocols to solid state. In solid state, as I said at the beginning, there are a lot of different interactions that you may have to take into account. So it's not as easy as simply saying, okay, now we are in solid state. So these are the 2 possibilities to continue this last work that I just said. And with that, I finish. I hope that it was interesting, and thank you very much.
No he encontrado eso en la biblioteca de Apple Music.
Thank you very much, Paul, for such an interesting talk. And now we have some time for questions. So if anybody has one, feel free to ask.
Hi. Hello. Hi, Paul. I have 2 questions.
Okay.
The first one is general, because I don't know whether I understood correctly, but in all the protocols you show, you manipulate also the molecule that you are trying to measure. For example, you apply a pi pulse on the carbon, or
exactly, yeah.
How is it possible to do that when you are trying to identify what molecule you have, or you are only interested in the interactions, or?
Yeah, that's a good question. So usually we work in the looking always at biological samples. So usually you consider that your molecule will have either hydrogens, carbons, nitrogens maybe, and I mean you will not target, for example, plutonium or something like that. I mean, these type of sequences are usually used in biological samples or for medical purposes or something like that. So what you can do is apply. Okay, you don't know what molecule do you have, but you know that there's probably hydrogens, carbons, and nitrogen. So you send radiation for the three of them, and if there is good, and if there isn't, okay, that radiation will not affect anything, no problem with that.
Okay, thank you. And the second very short question,
Yeah.
do you have concrete numbers on what is high field, like how many Teslas or micros?
Yeah, usually high fields in this context is, well, for example, for the simulations that I showed in the end of the talk, we consider 2 Teslas. But I think in the context of, for example, MV ensemble and the problems that I explained, I think that from 0.1 Tesla to 0.5 Tesla, you have already problems with that measuring thing if you don't use this kind of measurements that I introduced, that they introduced in this paper. So high field, from, I don't know, to be conservative, 1 Tesla to I don't know, 20 Tesla, if you are capable of applying that field. Yeah.
Okay, very clear. Thank you for the talk.
Thank you for the question.
Are there any other questions? If not, let me ask one. About the last method that you explained, does it work in all cases or can it fail?
Yeah. So I showed this method for only this molecule because it's, well, one of the ones that we simulated. For this one, we simulated as well, and it works as well. For all the cases, I mean, of course, there are detrimental effects here, and not everything is perfect. So we considered various different cases that have different properties, such as this one, and other cases. And in all of them, it worked. But this is very dependent on the molecule. So probably there's a molecule where this method won't work because of some reason. Because, for example, recall that in this sequence, we added these times right here, these transfer times. And these times, I mean, they are not arbitrary. You have to set these times to a specific value that depends on the molecule. So, and the larger this time is, the worse the performance of the sequence is. So maybe you have a molecule where the ideal value of this time is very, very long. So it's no longer useful to use this sequence and better use the simpler one. So in most cases, it works, but there are cases for sure where it won't work.
Okay, thank you very much for your answer and for your nice talk.
Thank you, for listening to me. And I guess that's it.
Yes, I guess so. So thank you, Paul.
Another question in the chat. Sorry.
Oh, I didn't see it. Sorry.
Okay.
Doesn't the rotation of the molecules affect the signal?
You mean the physical rotation of the molecules, I guess. Yes. Yeah. Well, in principle, the signal, that everything that I explained already considered that rotation, because if not, if say you are in a solid state, for example, there are other interactions, as I said, that actually those interactions get cancelled out thanks to those rotations. So in principle, everything that I explained is already considering those rotations, and all the interactions that I showed in the Hamiltonian are like effective interactions that arise from considering those rotations. So this Hamiltonian right here, for example, the full Hamiltonian already considers this case where everything is averaged out by those rotations. But if there are no rotations, this is more complicated. Did I answer your question, or? Okay. So thank you.
Okay, so now if there's no any other question, we can conclude the talk. And thank you again, Paul, for your talk and for all your time.
Okay. Thank you, you all. Bye.